So our next speaker is Marton Bognar, who is a PhD student at KU Leuven and doing research together with imec-DistriNet. So his research work is in the area of hardware design, side channel attacks, formal verification, both on the offensive and defensive side of the research. I always love you security researchers. Nobody else can pull off saying offensive and defensive in a bio, contributing to a number of projects on side channels. So the title of the talk is Proteus, an extensible RISC-V core for hardware extensions.
Hi, everyone. It's nice to see that there are still so many people for the last session. So I will be talking about Proteus, which is this RISC-V core that we developed at our research group, DistriNet. And the keyword is extensibility. So for example, when you think about RISC-V, the instruction set architecture, you think it's an open standard, it's an easily extensible standard. So if you want to implement your own instructions, your own CSR registers, it's very easily doable, as also evidenced by all the official extensions and also all the custom extensions that people have developed for their own custom purposes. So we thought it's nice that we have this easily extensible instruction set, but it would be great to have a CPU which enables you to take these extensions to the ISA and implement them easily in hardware, so that afterwards you can run some benchmarks, run some tests, do some evaluation, whatever your heart desires. So for this reason, we created Proteus, one of the many 32-bit RISC-V cores. So what makes this special? And how do we focus on extensibility? One of the things is that it's written in Spinal HDL, which is a DSL embedded in Scala. So even mere mortals like myself who don't know too much Verilog or VHDL can more easily get started with the development. I will have an example of Spinal HDL code later on in the slides. Even more importantly, the design of the CPU is based on a plugin system, which we took inspiration from VEX RISC-V, which was actually created by the same developer who created Spinal HDL. I will also explain this plugin system in more detail in the next slide. Proteus comes with two implementations. We have both an in-order simple 5-stage pipeline and also an out-of-order design with parallel execution units. And both of these pipelines implement the 32-bit integer and multiplication instruction sets and the CSR extension. Both of them pass the official RISC-V unit test, but we've also run more extensive cryptographic and benchmark codes already on both of them. And this is enabled by the board support package that we wrote for NewLib, so that you can just take C programs, compile them for Proteus, and run them on either pipeline. So let's dive into the details of this plugin architecture. I'm sure most of you are familiar with this pipeline schematic. So these are the stages that an instruction travels through during its execution. So we have instruction fetch, decode, execution, memory operations, and register write-back. You can also think of this pipeline as interactions between the pipeline registers. So between each stage, there is a pipeline register. And during the instructions execution, data travels through these pipeline registers. And in between, the stage defines some logic, some operations on this data that is propagating. And our plugins plug into between these pipeline registers. So basically, when you are writing a plugin, you can define, OK, I want to take some values from the previous pipeline register. I want to do some logical operations on it, some arithmetic, whatever you want. And then I want to write that into the output pipeline register. So here you can also see an example of some Spinal HDL code. In the first line, you can see that we take some input from the input pipeline registers, for example, the ALU operation. And then on the last lines, after performing some operation on it, we can just write this into the output pipeline register. And this whole thing is written in this abstract manner. So you can take the plugins and just plug it into whichever stage you want. And you can even modify this later. It's also possible to write plugins that modify multiple stages or that propagate data across stages in the pipeline. For example, this blue one represents a branch predictor, where in the execute stage, we look at the instruction that's currently executing. We check, is this a branch? What was the branch target? Was the branch condition met or not? And based on that, we can update a table, which is then consulted from the fetch stage, where the instruction fetcher decides, based on this branch history table, which next instruction it should fetch. So far, I've talked about the in-order pipeline, but as I mentioned before, we also have an out-of-order implementation. This features the textbook algorithm of Thomas Ulu to perform register renaming and scheduling of the instructions. But it's also reasonably close to real hardware. I will have a picture about that later. And what's great about this out-of-order design is that it also uses the same plugin system as the in-order pipeline. So we actually can reuse many of the plugins that were written for the in-order pipeline and just plug them into the out-of-order pipeline. This also means that if you decide to develop a new plugin, for example, for new floating point instructions or something along the likes of that, you can immediately test it out in both the in-order and the out-of-order setting. So you can get an idea of how your extensions would have an impact on very small embedded systems or in higher grade, more complex CPUs. This out-of-order pipeline is also configurable in quite a few parameters. For example, the number of reorder buffer entries, the number of reservation stations, the type of execution units you use. You can also switch out what type of branch prediction algorithm you want to use, and so on. Here, I'm bringing you the cutting edge of desktop technology. This is a picture about the architecture of the Intel Core 2. And if you squint hard enough, you'll see that this is basically the same as our out-of-order implementation. So both of them feature fetching mechanisms, then instruction decode, then some reorder buffers, quite a few execution stages, and then finally a retirement register file. So the idea is that if you develop a plugin and you try it out on our out-of-order execution pipeline, then you can get an approximation about how this would impact real-world higher-end designs. Let me give you some concrete examples of the extensions that we have developed. So I already mentioned that we have multiple different branch prediction algorithms. You can switch these out as you want. We also have multiple research papers that we implemented on Proteus, either on the in-order or the out-of-order pipeline. For example, we implemented most of the cherry instructions, which we had some talks and posters about already. This was used in a research project called Cherry Tree, where we used these cherry instructions to build a trusted execution environment. And this is going to be presented at EuroSMP in a month. Another extension that we developed is Prospect, which is a mechanism for secure speculation. This will be published at Usenix this year. And this one was obviously implemented for the out-of-order pipeline, because that's where we have out-of-order execution and speculation, which is needed to be able to test out this security mechanism. And actually, tomorrow in the Orshin workshop, we have a talk about this Prospect architecture, if you're interested. Orshin is the European project that funds this research partially. And we also have some contact with people who are looking into extending Proteus with some non-security proposals. So all of the extensions that I mentioned so far are security related, but the idea is that the CPU is extensible in general, not just for security extensions. Then on the first slide, I had a work in progress indicator. This is because we still have quite a lot of work that we have planned for Proteus. One of it is that this plugin design of plugging into stages works very well in the in-order pipeline, but on the out-of-order pipeline, it's not as extensible as it could be. So we would like to iterate on that further and make it even more extensible, even in the parts of the dynamic pipeline that do not relate to stages. We also don't have the best performance yet, but it would be interesting to optimize this a bit further. And then maybe Proteus could move from just being a prototyping architecture to something that could be considered for actual use. And we would also like to implement some additional features that would enable us to boot Linux, which is still not possible. And that's already the end of my talk. So I would just like to finish with inviting you to get involved. If you're planning to implement some kind of security extension or non-security extension, then get in touch, and I'm sure we can talk about it, and we'll see if we can help you with it. It would also be very useful for us, because the more extensions are implemented on Proteus, the more we know how you can make a processor that's easily extensible for different purposes. And you can see our repository on the slide, so if you go there, you can find all the installation instructions and some example code. We also have a Docker container for easy setup, because I know that with certain open source projects that can be a bit difficult to get started. Yeah, that's it. Thank you. Are there any questions? I think everyone wants to go home already.
I tried before. All right, thank you for your talk. Very interesting. And